Okie dokie. Well, good morning, all. Welcome to another spring showcase. Today we are partnering with Radio Data Networks and Anglian Water to find out more about making sewer and drainage networks smart. And we're excited today to be live streaming from Radio Data Networks at the Innovation Farm, an eco-friendly innovation hub for the water industry. So thank you guys so much for joining us. My name is Chloe Tooth and I am the Comms and Engagement Manager here at Spring Innovation. For those of you who might not already know, we are the Innovation Centre of Excellence for the water sector, supported by all the water companies across the UK and Ireland, as well as the supply chain and academia, with the goal of enabling collaboration, removing duplication and accelerating innovation within the water sector. So we are the custodians of the Water Innovation Strategy, and bear with me. Clicked off my screen. So for anyone that hasn't seen that document, we're going to be popping a few links in the chat to that in a second. So it lives on our website. It has 7 themes with challenges that sit under those themes that we want to be solving within the sector. So we also put out calls for innovation against those themes. So through our Spring Accelerator, at the end of this month, we are launching our next accelerator program inside Water Innovation Strategy Theme 3, Protecting and Enhancing Natural Systems. So looking specifically at catchment management. And you can find the Ambition Surgery recording, the conference that we held to help define our challenge, on our YouTube channel. So I'll make sure there's a link to that in the chat. And be sure to follow us on LinkedIn to see the call for innovation when that goes live. So today's service offering is about knowledge sharing. So we have 2 aspects to that. The first being our knowledge library on our Spring platform, where there is a bank of over 45 case studies for you to go and learn from and utilise on the innovation projects from across the sector, with over 200 more case studies in the pipeline. So this is being constantly updated. So please do go over and register and check that out. And there'll be a link for that in the chat also. So as I said before, the showcase recordings for a number of those projects and today's project, and any supporting links or documentation will also sit alongside those case studies. So this is a 2-hour knowledge showcase event where Radio Data Networks and Anglian Water will do a deep dive into how you can reduce sewer flooding and pollutions by adopting smart network solutions, sharing results, lessons learned, and overcoming the challenges faced along the way. So we are happy to see there are over 124 people registered for today's event, with representatives from Norway, Singapore, India, and Spain too. So for any of those that have made it, welcome to the call and thank you so much for joining us. So today you're going to learn a little bit more about how you can utilise this technology as part of your solutions portfolio to sewer flooding and CSO overflows. So this is showcase number 16, and with over 2,000 people registered for these events in overall, we're super happy and really proud with how these events are helping disseminate knowledge from these innovation projects and accelerate learning across the sector. These showcases are all about being able to learn a little bit more from the project, taking away those learnings and that knowledge and being able to embed those in your organisation. So this being said, we'll be launching a poll at the end of this showcase to find out how interesting you found the information and also whether you're hoping to go away and use that afterwards. So please do submit your answers at the end of this event when that comes through. So on to today's session, I'm just going to run through the agenda and introduce our speakers before I hand over to Brian to kick off this showcase. So initially, we're going to be doing the introduction to the speakers, going to the value of the project, a little bit of context and further information. We're going to go into a quick break and then into a live demo and lessons learned, and then into the Q&A section at the end. So if you do have any questions, please make sure that you're popping those in the chat and we will do our best to answer as many of those as we can in the Q&A session. And if for any reason we don't get those questions answered, we will be getting those answered and popping them alongside the case study and the recording on our platform. So I do apologise if we don't get through all of those. And then on to the speakers for today. So we have Brian Back, the founding director of Radio Data Networks, and we have David Singerton, Innovation Projects Manager at Anglian Water. So without further ado, I will pass you on to Brian and we can start this showcase. Thank you again for joining us today.
Good morning, everybody. Very pleased to have you on board, and we are in the session where we're going to accept lots of questions, expect lots of questions at the end of this. So obviously, as you go through this, we much appreciate you make notes of your questions later on, because it's easy to forget what you want to ask. But I want to start with a pause for thought. And it's a statement I heard recently at an event I was attending in London about engineering. And it was actually a simple phrase, which was about what God didn't create was created by engineers and scientists. And that was a quote from the late HRH Prince Philip. And obviously, don't forget, this would include our sewer networks, which actually do date back actually to 2,000 years ago, because they weren't actually also created by ourselves in the modern generation, but were created also by the Romans. So that's my pause for thought. I'm going to now hand over to David, who's going to set the context of what actually this project's about.
Thanks very much. Welcome to everybody, and thank you for coming to listen to us. The background to this piece of work that we engaged Brian with was related to establishing a way of managing the flows that arise from new developments. And everybody's aware that when houses are built, they generate flows, and those flows have to be captured within the sewer systems that we already have. The problems and issues that we have with our existing sewer systems are that have restricted capacity, and obviously adding to that capacity, adding to that the load onto the available capacity can cause higher surcharge levels. And might mean in certain cases flooding and potentially pollution could occur. So we wanted to find an effective and inexpensive way of controlling and managing flows into the network, which didn't include large capital construction such as building pumping stations with wet wells, etc. One of the things that was a key concern, and it's very prevalent at the moment, is the need to manage and, if possible, reduce sewage pollution. Obviously, there's an Act of Parliament in motion at the moment, with water companies having to focus very carefully on how we manage and control what leaves the CSOs, combined sewer overflows, and we're looking for all ways and means possible to reduce the operation of overflows that's affordable and effective. And obviously, one way and means of achieving that is by putting flow control valves into the system. A secondary benefit is obviously if we can reduce or manage flow better within the sewer network, potentially we can reduce and better manage flooding. And flooding is very, very important. Obviously, we want to reduce that wherever possible. And with climate change and the difference in weather patterns over the recent years, it's something we have to sort of keep front of mind. One of the further issues we have to consider is what passes through the sewer networks in terms of things like microplastics, inorganics, organics, pharmaceuticals and other things. And the ability to control and manage the flow in the sewers can mean that we can contain and curtail the operation of overflows, preventing some of these pollutants actually leaving the system and pass them through to our works for capture and treatment. That's a serious consideration. And ultimately, what we want to do is improve water quality. And we've worked with groups across the Anglian region, and the intention is to better manage our sewers where possible with low-cost, effective solutions to enhance the environment, but particularly collaborating with the users of river water and bodies of water so that they are aware of what we do and how we do it in a better, more sustainable fashion. The state of play at the moment within water is 2020 that sewers CSOs operated more than 400,000 times, which isn't a great state of affairs. However, as they are necessarily release points for the flows in sewer systems, we don't have any alternative, but we can do better in terms of controlling, managing things like first valve flush component and keeping a lot of the contaminants that otherwise might escape within the system, and the control valve arrangements that Brian's come up with can help us achieve those end goals. So the particular case study of interest that we have is a place called Burnham Road at South Woolham Ferrers. It's a small town, and the case in point was that there was a development of a commercial and healthcare arrangement where we have an Argos and Sainsbury's being built, which obviously gave rise to an increased flow from that catchment, subcatchment, into the existing main sewer, which was already hydraulically overloaded. The valve was a very suitable and appropriate way of managing and controlling flows, and Brian was asked to sort of investigate the opportunities to site and locate that valve, design the valve to suit the purpose, install it and make it operational. I'll hand over to Brian, who can talk about the design challenge.
Well, thank you, David, for setting the scene. As David mentioned, it is an absolute challenge, and what we're up against when we set these sort of challenges are we have to make everyone, all the people in the industry, happy and content that what we're going to do is not going to make a bad situation worse. And also we're trying to look at so if you look at the ingredients to make success out of this particular project, we've made it akin to a cooking bowl. You're putting the ingredients in the bowl, and these are basic things that you will need to make sure the project's successful. Obviously, the overarching thing is it has to be affordable. And affordability comes out of how we implement the design, so how we approach this whole concept. Because David's mentioned a valve, and if we were to look at fitting a traditional penstock, for example, that would require building the new chamber, bypassing flows, all those sorts of expensive processes. And one of the key things with this particular design of the smart network elements was trying to avoid those particular constraints. One of the key things also is not to go down the route of civil works, because it's easy to say, oh, just make sewers larger to take all that extra load. But even if you did all of that, apart from the carbon intensity of doing that particular part of the process, you then move the problem to the works, which then cannot cope. So it's not a simple solution. What also is key with these types of projects is to implement a design where you don't create disruption. What you don't want is lots of days of civil works, digging up roads and so on, to put new sewers in or new chambers, because that's very expensive and also cause bad relationships with neighbours. One of the key elements also in this design philosophy was to eliminate the need for overpumping. Now, David mentioned the Southwood and Ferris as an example. When we actually arrived first on site, the chamber had already been constructed, and this was a sort of an afterthought. The fact before the store could open, the flow had to be controlled. So it was a case of installing this equipment in a live working sewer without having to overpump and bypass, which is very critical. And also with the design philosophy, we had to make something very space efficient, because if you start occupying land and territory, you're going to then reduce the need for the space available for affordable housing. So there's lots and lots of constraints coming out of here. The current thing, of course, is something that's occurred since we started this back in 2018, is low carbon. This has become even more so, and that covers the entire process, from a cradle to grave philosophy, from the design, the manufacture, the installation, the operation, to right up to the end of life. And what goes hand in hand with this, which is one of the learnings we had from one of the previous projects we built for Anglian Water, was the need to eliminate the need for mains power, the point of control, and also the point of sensors. With the first ever regulator we built back in 2018, we found one of the biggest constraints was getting mains power to the location of the kiosk. So this was a major constraint we've addressed by making everything, as you'll see later in the presentation in the demonstration, solar operated. So it means you can install these types of interventions anywhere, and actually then have a long-term low carbon footprint in operation. One other key thing is everyone talks about AI and smart sensors. The means of control, when the level is high in the sewer, you want to inhibit flows, restrict the flows and so on. One of the key elements, of course, is in red at the bottom. You need real-time data, but also you don't want to restrict what type of sensors used. Sensors are in evolution, so it's an open standard for the control method that can control this type of regulated device we're going to talk about. And the final thing, it must be fail-safe. The whole design by its nature has to be fail-safe. If something was to go wrong, you must not make the situation worse than it was. And intrinsic safety goes without saying. Where we have high septicity, there could be a potential risk of explosive gases in the sewer networks. So ATEX, or UKEX as it's called now, has to be considered. Cyber security, again, is also important, which leads on to something that we're going to talk about as well. The system needs to be autonomous in operation, so it's not dependent upon the internet, which also gives you a guarantee of longevity, because technology will move on. As you would see in the cellular networks, you can't rely on a thing to be static for very long. But if you make an autonomous system, you have the ability for it to operate on its own from now and into the long distant future without the need to change too much. So as I would say, don't put all your eggs in one single basket, because you don't have a central control, have a distributed control at the point in the network. Another thing that's very important as well was, and it has always been stressed to us, is the minimal need for maintenance. And this is something that, again, we've tackled. We've reduced maintenance because the actual device you'll see in a moment is a self-cleaning product, but also it has the ability to be removed from the network without the need for confined space entry for cleaning and test. And finally, we have to interface with existing SCADA and telemetry so the utility can get feedback about the operational status of the device. And what goes without saying, retrofitability, as in the case study that David's just mentioned about the working with the existing systems is key, because this was already built as a sewer network. We had to retrofit into the existing sewer chamber. So I'm introducing you now to what we call the wastewater flow regulator, but most people in the industry seem to call it a sewer flow regulator, which doesn't particularly matter. It has actually been granted a GB patent back in 2022. And the theory is as follows. So if you took the example of the Southwood and Ferrers development, where it says up on the left-hand side housing, there's a pincher in the yellow of a regulator valve. You've got the point to open, you're then restricting the flow back into the main sewer. And this is the actual part that fits into the sewer. This is the sewer flow regulator. And you have a body at the top, which is placed into the sewer over the benching and the invert. Because one of the key elements here was that we didn't want to be evasive. We didn't want to create any issues about the potential for ragging. So no discontinuities. So this is where we differ substantially against a penstock, which would require a frame and a new chamber and a weir wall to be created. This actually utilizes, I'm clicking back and forward on slides here, utilizes the existing chamber, the existing invert, the existing benching, and is designed to fit the actual existing chamber and the benching and so on. It's got two guides in there, which actually let the control element, which you'll see in this picture here, be inserted and removed for servicing too. So what you have is what we call the regulator blade and actuator. And at the moment, this is in the illustration here, there's a 150mm one and a 225mm blade. Now, as you can see clearly in the top left-hand picture, in the open position, there's no obstruction in the invert at all. We haven't created any discontinuity to attract fat oil and grease, rags, dead detritus, and so on. So the probability of this blocking is no greater than an open free-flowing sewer. On the right-hand side, you can see a picture of the actual regulator closed. As you can see, it's like a tongue that's gone into the invert, and it's actually using the base of the invert as part of the seal. So blade up, open flow, blade down, restricted. Now, we mentioned the need for solar. That's absolutely paramount, and that's been used on the majority of the flow regulators that have been installed to date. It does give the ability to install them virtually anywhere. The only constraint is you don't want to be overshadowed by trees or tall buildings. But inside this particular control kiosk, as you can see here, you've got the solar panel at the top. You've got the sequence control that actually controls the operations of the actuator underground in the chamber. And this one includes radio telemetry, which talks to and from the wireless sensor down in the network, and also back in this case to Anglian Water's telemetry too. It also has manual local controls, so you can actually test the unit on site as well. If you look at the control philosophy, it's very simple. If we took the case of this as an analog level sensor, such as a Vega radar in the sewer, perhaps a kilometer away, radio telemetry would bring that level back to the control point in the controller, and a threshold would be set upon which the regulator blade opens and closes, inhibiting or enabling the flow. Obviously, in the open position, the flow is enabled. In the closed position, the flow is inhibited. So if you look at typical system topology, on the right-hand side, you have a level sensor. It could be any type. The system is very agnostic. It could be a float switch. It could be a velocity sensor. It could be a higher level radar with a trip amplifier. It can be any type of sensor. It, as I say, is completely agnostic. The flow regulator could live several kilometers away at the actual point of the new housing development, for example, or the new industrial or commercial estate. And the control point, the control is then implemented to reduce the flooding potential at the hotspot.
Hi everyone, so we're just going to go to a quick 10-minute break, which will then be followed by our live demo. So join us back in 10 minutes time.
Okay. Well, welcome back to the Innovation Farm. As expected and predicted, it's raining again. And we're going to start off with just showing you typically what the installation would look like above ground. This is a typical solar kiosk, but excuse the rain, of course. And this is it basically inside the one you saw in the picture earlier. What we're going to do, though, however, is actually run a live demonstration, because it's a little bit more challenging, inside our innovation barn using a flow rig to simulate an actual flowing regulator. So ignore this for the moment. We're now going to go inside, so follow me through with the camera. Innovation test rig area. And I'm going to introduce you now to a so this is going to be our main sewer, which has a capacity problem. We'll start a little pump here to illustrate the fact that the sewer level is rising. So this is going to be our main sewer. Over here on the right is a flow regulator. This is a 150mm one, actually built into a plastic invert for ease of demonstration, but the inverts can be concrete too. They don't have to be plastic by any means. This one actually will show you how it's actually built correctly and installed correctly. And what we're going to do is show you how this system works as a real live demonstration. So we've taken the controls out of the green kiosk and shrunk it into the compact version, which is the one that we use if we're going to install the controls inside someone else's kiosk. If there's an existing kiosk by the side of the road, they can go in there too. So it is actually quite a compact installation. What's very key about this installation here is the flow regulator sitting over the invert. As you can clearly see down here, there's no discontinuity, nothing changed itself. So the chance of attracting rags and so on is minimal. We're going to just make the demonstration more realistic here, because what we're going to do is put a flow on in our sewer. You can actually see we have now a flowing sewer. Obviously, as you can see, the flow is going through here unabated. You have an overflow pipe here should things go wrong. So this is cut off to the height of the store point. What we're going to do now is actually let the sewer level over on the left-hand side rise. And what we have in the sewer here, but it could be any type of sensor. We have first on the left here is a Vega level sensor, which is actually connected to a radio telemetry transmitter. Every time you see the blue LED flash, it's taking the latest level and relaying it wirelessly back to the control kiosk. I know this isn't very far, but technically speaking, we can have this 5 kilometers away. The level's been reached now. So the level in the sewer reached the threshold. The green light that was on here, you can see, has gone now red. And what you see now is the flow has been restricted by the regulator, which is closed in the invert. So it's actually sealed. Now you can hear my little electric pump now is running dry because it's been starved of water. So I'll switch this off here. And now what will happen is we'll ask the team over here to switch off the pump and let the level recede. So the level in the main sewer will recede. Now just imagine now that the rainfall event is now finished and the level is going to gradually drop. While we're waiting for the level to drop, I'll talk about some other features in here. You saw in the illustration the guides. These are the guides here. And what this actually enables is if you turn the lock to the left or right here, you can actually take out the regulator. Now the level is actually dropped. And as you can see there, the flow was retained and now has been let go. So we're now back into a flowing system. So we can run around the system again. But you can actually see now we have an unobstructed flow path. But what you've actually got also is the ability, when this is in the raised position, to remove it for service from the surface. So you have a long key and 2 hooks that go either side, and you can actually lift the regulator clean out of the actual frame. So the frame stays in place. And what it means is you can service this from the surface. This applies particularly well, works particularly well in shallow chambers of up to 2 meters. You can lift the regulator out, lower it back in for service and maintenance, should that be needed. The other key point, which is part of the patent, is the fact if this was ever to get stuck, you have the overflow weir here, which is a standard piece of plastic pipe that you cut off with a spill point. You cannot surcharge upstream should anything go wrong. So that is basically the system in action here. This is the flow, and we can take you outside again if weather's. Yes, my colleagues quite rightly reminded me. We have been asked, can this be used for flushing? And indeed it can, because as you saw there, if you close it in this flow, and then reopen, you get a flush, which is great for first foul sewage removal. So you get the first foul flush, it helps to reduce that particular problem. So you do have an extra benefit of having the system in here. And alternatively, this blade doesn't have to be a full seal, it can be partial. So 50% of regulated designs that are either proposed or installed aren't restricting the flow totally, they're providing a partial stop. And people have said this is a better and safer alternative than using a hydro brake, which for small size sewers could be quite small and is liable to clog. So there's certain aspects and certain benefits of this design above and beyond what we originally conceived. So if we walk back outside, weather permitting, we have a second live demonstration. And this is using the kiosk outside. Now, this is totally a solar powered operation. This has been out here for several months, waiting to be demonstrated just to prove the point that solar is very viable, even in the UK. In fact, most of the systems we have out there in service since 2018 have been running successfully on solar. I'll open the door briefly because of the rain, of course. And I've got a colleague over in the chamber over the distance over there yonder, and he has got a float switch. So we're raising the float switch up. That has now been relayed by radio telemetry to the chamber. That now goes to the regulator, which has now actually got some water in it, thanks to the regulator. So this is was going to be a dry demonstration. It's now a wet demonstration, but we've actually got a level in the chamber. And this is a larger model than the one you saw earlier. The one you saw earlier was a 150mm one. This is a 225. Exactly the same principle, same scale. Important to note is the shape of the back wall. This one's a square back wall. That one is back wall. But we actually custom manufacture these to order to suit any back wall or any angle as they come out. If you could kindly lower the float, please. So we'll have the regulator open again. It's always a small delay, waiting for the telemetry to work. There we go. You can hear it click over in the control kiosk, and it just takes a few seconds, and then the regulator blade lifts. So as I said earlier, it doesn't have to be a full closure. It can be a partial closure. And the larger the invert, the better they are when it comes to using the partial closure devices. But again, as you can see clearly here, perhaps clearer than the version inside, what we have is no obstruction whatsoever in the actual invert. That's very key. Now that really ends the outside demonstration, a live demonstration that actually worked. Often you get a lot of demonstrations where whatever else happens, something always goes wrong. Today, apart from the weather. So thank you. We'll now move back inside.
Welcome back. I trust you saw the live demonstration outside. A little bit wet now, thanks to the rain. A little bit smeared up on my glasses, but that's one of those occupational hazards with the UK. What we are going to do now is move on to, we have a slight technical hitch. Okay, the mouse is now working. We're going to talk about this case study in greater depth. So David mentioned earlier, quite rightly, there was a plans back in 2018 to build this housing development, or not housing, should I say, this new commercial development, which is actually, if you look at the area occupied by the yellow rectangle, is quite substantial. And you have this sewer hotspot. So we've illustrated earlier that radio telemetry can be used to control the regulators, and indeed it was of this application. It's about 1 kilometre as the crow flies between the hotspot, in inverted commas, and the housing development. So if you're planning this type of intervention, the first thing to do is identify your hotspot and then work out where you want to put the controls. Now, one thing that has to be emphasised with this new development, Anglian Water were fortunate to get in early on this development to actually specify or suggest to the developers that they would build these sewers with slightly oversized pipes, because apparently lane sewers are 300mm compared to 150s was negligible difference in cost. Obviously, you've created larger capacity by doing so straight away. And then the challenge is restricting the flow on the outflow. And the options of having orifices and hydro brakes and so on wasn't viable. So we're back to where the regulator comes into its own. So you can see in the illustration here, we have the yellow valve symbol illustrating the point of where the site exits and joins the main sewer, and the blue triangle indicates where the actual sensor was put into the network to determine the level. The challenge is then if you take this as a challenge in the sequence, you have to measure, and to obviously measure up and find the actual, first and foremost, you have to make sure whatever you design and will fit through the existing covers, which is typically 50 centimeters. That's your first overall constraint. But the main constraint and challenge is actually fitting the invert, because as you can see, as every invert's different, it's not as straightforward as the illustrations you've seen earlier in the demonstration. These are not perfect by any means inverts. So the things you have to gather is to make a template of the shape of the invert. So you gather that information, so someone will have to template it. You have to determine the angles and also the position relative to the actual chamber, because more often than not, the actual inverts will not run necessarily through the centers of the chambers. They're slightly offset or can be slightly offset. Also, the angle in which they enter and which they exit may not be at right angles to the chamber, but all of these can be taken into account with the design. The final point is to determine what is the critical height that you can tolerate if something should go wrong. And as I showed you in the demonstration, you have the overflow pipe is the height at which you cut that overflow pipe off to prevent spills and surcharges back upstream. So they're things you need to gather at this early stage. The next step is to prove that the control point is viable too. Can you get a radio telemetry link back from the point of control? And that requires a field survey where you put up a test transmitter, you measure the radio propagation across the link, measure the signal strength received at the control point to prove that you can get a real-time telemetry link. Because one thing that's not very viable to do is to rely on the cellular networks, because you do need that point-to-point direct communication link, and preferably something that's very fast. What you don't want is 15-minute data, because that may be too slow. Preferably you want minute-by-minute data, as you've seen in the example on the demonstration, where we had a live feed from the radar sensor. So we take all that information on board and we then produce the actual design. So each regulator is slightly bespoke. As I mentioned earlier, the benching will be different heights of the benching, the back walls will be different, the curvature of the chamber is different. Some have square walls, some have flat walls, and so on. We have a number of techniques to take out all the undulations of back walls, which include what we call compression rings, which make the gaskets have compression points similar to cylinder head gaskets on cars. Similarly, we can apply the same approach to the benching, and we take out most of the imperfections of the benching. And then we have a technique which we call benching ears. It's a funny term we've coined recently, but it's a modification to the bottom of the chamber, which enables the imperfections of the benching to be taken out, where someone's hand benched it. And it lets you fill in that tiny top corner, because otherwise you'll get too much leakage past the regulator. But what's really key is the whole design can be modeled in 3D and offered up and given back to the customer for approval. So you can have a check, cross-check, and so on. And using this philosophy has meant that every single regulator we produced to date so far has fitted first time, not just through the chamber, but also through fitted onto the benching snugly first time, and that's been very important. What also is important, and perhaps something we haven't mentioned before, is the actual weight. If you can see the design earlier, it splits into two parts, and on all occasions, cranes have not been necessary because each item's been under 10 kilos, so it's actually helped assembly too. And that may be one of the questions that comes up in the chat. Obviously, if you build them larger, then they may get more substantial, but in principle, so far, they've been quite lightweight, easy to manhandle through the chambers and to install. The choice of fixings, again, is down to the utility, and also the spacing away from the edges of the invert is also something that you can choose too. So there's a lot of flexibility because all of the systems are made locally in the UK. So the manufacture stage is in the next part of the process. So we assume now the client has agreed, they like the fit, they like the concept, they like the actual design, and they feel that it's going to do the job for them. The regulators then are fabricated. They're actually fabricated in Essex with steel fabricators using coded welders. All the products are made in stainless 316. or 304, depending on the type of sewer we're dealing with. So if it's surface water, it's 304, 316 for foul sewers. And once welded and so on, and then that's tested and ready for installation. The important part, of course, is then in parallel to install the kiosk. So you saw the kiosk in the demonstration outside, and that only requires a duct to carry 2 air lines back and forth to the chamber. So you have an air line that's used to drive the actuator up and an air line to drive the actuator down. So those is the only requirements. So you don't actually need a duct to carry mains. So it's not necessary in many cases to dig the duct very deep. So you don't have to go to 18 inches because there is actually no power in the chamber required at all, which is another benefit we perhaps didn't mention earlier. And simultaneously, whilst you're installing the kiosk, also you can fit the level sensor down in the network. And this, as I mentioned earlier, could be any type of level sensor. It doesn't require anything specific. All the control kiosk requires is a closing contact to close and an opening contact to reopen the regulator. So it's designed to be agnostic. It could be any sensor. It could even be controls from telemetry. So if the utility has, for example, a model which is actually live and has indications that the levels are going to be high, you can actually preempt an event by closing the regulator also using remote control rather than making it autonomous. So you have the ability to do both. This also means that the utility, should they wish to, can test the regulator periodically by opening it and closing and looking for the feedback. So there's a lot of extra features that haven't been mentioned earlier, which are coming out now during this installation process. If you look at the actual mounting now, this is in the early stages of installation. This is before the overflow pipe has been installed, but this is the actual regulator at South Woodland Ferrers. As you can see, it's a slightly offset invert. The benching here was very, very basic and was corrected by the bench engineers. And you can see here that it's been partially bolted down and air lines run into the chamber. So you can see the blue, which is the opening, and the black, which is the closing lines. And this one has got flow in there. So it's been installed under flow, no need to pump out, drain out, and so on. And it's about 2 meters deep, just to give you the context of the installation. The back walls can be filled and sealed using compressible foam gaskets, or alternatively using standard benching or mastic seals. Again, there's not particularly any hard and fast rule. So any particular utility has a preference to whatever they use in chambers, then we can accommodate that too. The final part of the installation is obviously the test and verification. This is something that's obviously conducted by the utility. And you can see now the site has been cleared, the kiosk is installed, the system has been commissioned. In the foreground of this picture is the little manhole chamber in which the regulator lives, and the cable duct is now invisible below the grass. And in the background, you can see the large superstore. So in the background, top left, you can see the large Sainsbury's. Out of shot to the left-hand side is also a very large NHS walk-in centre as well, which are all served by the regulator. So that's the design, that's the principle, that's the installation process. It is not that long. It's not compared to, for example, installing a penstock, which would have required a new chamber. If it was in a street, you'd have had to close the street, you'd have to sink the chamber, you'd have to build a new chamber with a weir wall, install the penstock, and most importantly, you'd need mains power. This did not need mains power. So this is a totally net zero, off-grid, autonomous system in its operation. So we now move on to lessons learned, and this is something myself and David will share this particular session on lessons learned. We found that obviously from our personal experience that one thing for certain we found was that all inverts are different and the quality of the benching varies tremendously, because it's something when people bench an existing sewer network, it's something they don't really consider about. All they look at is to really contain the flow within the actual invert and to make it so that anything that comes out of the invert will go back into the invert should the levels recede and not be left on the benching. What we're trying to do is actually convert that curved invert top section, or the benching top section, into something square. So that's why I mentioned earlier we introduced benchineers, which actually square up the invert in the region where the regulator is. And the regulator in this picture is actually installed on a Y branch invert, but it is the same size as the one at Southwood and Ferrers. It just has a better illustration of what I could call poor in benching. That's one of our first learnings. And the second one really was that a lot of people are now asking for partial closures rather than full closures. And also they want to have a system where they can utilize some of the existing chamber to provide storage. So rather than mounting the regulator, as you saw earlier, on the back of the chamber, it's also equally viable to mount it on a weir wall within the chamber. And this is an illustration we've taken off our CAD system of 2 proposed systems for certain utilities. And this one has a partial closure regulator. So it's equivalent to having an orifice that's actually able to adjust itself dynamically, and a weir wall behind it. Whereas if you notice in the top of the weir wall, there's a little cutout in it. So should it ever overtop, it will not pour over the top of the regulator. So it will be in a controlled fashion. It will actually spill over the top. And the weir walls, again, could be built as high as you need to stop sewer surcharging upstream. David, have you got some observations you'd like to add to this at this stage?
Absolutely.
The lessons.
Obviously, we have fitted a number of these valves in our business, and to date they've been successful. Haven't caused any problems in having been fitted, and have done a good job of work. There are a few, however. There have been comments from our operator regarding the robustness of the valves, obviously, and their longevity. And we have happy to report that we haven't had any problems or issues in terms of any failures or repairs necessary. And as Brian mentioned earlier, that they are actually relatively easy to remove and service, so that's gotten good thumbs up from operators on that side. The concerns we mainly have relate to how they're operated and when they're operated, which links back into the smart networks elements. When we fitted these valves in initially, we were trying to solve particular issues in specific locations to manage flow, but what could happen and can and probably will happen is in the future we'll put these valves into sewers where there are flows that can be managed, where there is latent capacity available currently unused or not used fully in times of wet weather, to the greater benefit of the wider system. But what that would require is that the valves be able to be operated as part of the control philosophy suitable for managing wet weather flows which would otherwise cause potential flooding in certain parts of the catchment, or to prevent or enhance the operation of overflows that could cause pollution unnecessarily because of capacity restraints at particular points in the sewer network. So we already have a system called sentient catchment, which we employ at Great Yarmouth, and that incorporates a number of valves under with use of a digital twin representation of the sewer networks, where the valves can be automatically operated on demand with knowledge of the flow within the sewers. An added factor there is that you do have to have an understanding of the flows within the sewers from sensors set up and sited at appropriate locations, detect the surcharge levels, which become critical for operation of such things as CSOs, and integrate that understanding into a wider representation of how the system is performing, so that the valves can be actuated to control and manage flows to make best use of that available capacity. One particular thing that's of interest and noteworthy for current regulations that are in place, talking about Section 81, Section 82 of the Environment Act, where water companies have to pay heed to what is being discharged from the CSOs in terms of impact on waterways, receiving waters, causing pollution, is that there's a possibility of better managing first valve flush component, and use of these valves at specific locations where we have CSOs can actually curtail the flow that leaves the CSO at point times through storm events, and reduce the polluting effect by allowing the polluting content, the first valve flush, to pass through to the works rather than pass over and out of the overflow, and then restore the overflow back to full operation once the storm and the first valve flush has passed and the storm starts to subside. So they do have possible future opportunities to improve and enhance river water quality on top of better managing flood and flooding. So that is something we're considering as part of this as a tool, as part of a suite of opportunities to improve the operations of our sewer networks.
Yes, well, thank you, David, for that one. And that sort of leads on nicely to one of the other applications we've used this type of technology for with Anglian, which is CSO dry spill containment. Equally, this is a viable solution using this type of technology. So if you took a CSO overflow, you can actually fit a containment weir, as we would call it, on the end of the discharge pipe. And effectively what it does is it raises the spill point. So as David mentioned earlier, first foul flush could be diverted to the works using that technique. Or equally, if you detected using your sensors and smart network that you've got an abnormally high level in the sewer because of potential blockage, it gives you time to contain that foul discharge within the CSO discharge pipe and time to get a tanker out there to remediate the event. So you actually could turn an incident into a non-incident. So effectively, you're going to be able to capture that sewage before it's actually spilt into the environment. So there's other techniques and methods around this where this technology can be applied. And it's really down to the viewer's imagination, really, to think about where have you got hotspots in a network, CSOs that spill too regularly, areas where you get lots of blockages that cause dry spills too often, where you could deploy this type of technology to improve the water quality, receiving water performance, and reduce pollutions and reduce sewer flooding. The applications are absolutely endless, and obviously it's not the magic silver bullet for every application, but certainly in areas where you have these issues, I'm certain there's an application that these can work for. Have you got any thoughts on first foul flush diversion weirs, David, at all?
There are all sorts of opportunities and permutations, as Brian's mentioned. Yeah, obviously he touched upon the idea that if we're having a blockage or partial blockage in sewer networks, the valve won't automatically detect that itself at all parts of the network. It can, whether the sensor that's actuating the valve has been deployed. However, if there are other parts of the network, maybe further downstream or even upstream, it wouldn't be aware of that. But the idea for the future is to link the understanding from the data that's provided by the sensors together, so that we get to effectively a way and means of achieving a data set that can be used for data mining purposes, for contextual analysis, and from that set of data in the context of in terms of what's happening flow wise in the sewers, we can make some decisions. So an inferential decision making system which is both predictive and preemptive can be employed, thereby sort of taking into account what future weather might be occurring in terms of rainfall and its impact on the system, how the system's performing, behaving under those weather conditions, comparing it to what is expected in relation to what's actually occurring, and making better use of the control valves to control and manage the flow through the sewer networks to reduce the possibility of flooding and escape from the system unnecessarily. So there are a huge gamut of opportunities available, but this type of approach is often now considered to be best used with the wider control possibilities from things like the ability to use pumping station wet wells and the pumps within the wet wells to push forward flow, to sort of preempt and empty things like sewer networks and drain them down before wet weather events hit, and create make virtual capacity into real capacity within sewer networks for the good of all, both the performance of the works and also the quality of receiving waters when discharges do occur.
Thank you for that, David. On that subject, is one of the things that perhaps we haven't mentioned earlier is the communications between the sensor in the street and the control point. What we've done as a business is we've actually got a license from Ofcom, so we actually broadcast the telemetry over a secure private radio channel. This has proved very successful. Anglian's is one of the many utilities that actually utilises this channel, and what we have the advantage is we can actually transmit as and when we want, as frequently as we want, using this channel with great penetration through buildings and obstructions. Because one thing that is essential for this system to work and work successfully is to have a complete communication path that's direct from the sensor back to the control point. And in addition to that, you have the ability to control remotely. So you have the ability to have local control from direct sensor straight to the control point. And in parallel, you have the ability for central control to dial into the system and control it remotely too. So as David mentioned, you've got the ability to have a smart network, AI-driven smart sensor type virtual sensor, the digital twins controlling the network. Equally, should things go wrong like a blockage, which they cannot predict, you have the sensors in the network which can pick up and take over and override and say, sorry, the digital twins are not quite right. There's something wrong with the network. We need to take an intervention now. So you can have the best of both worlds. And being an agnostic system, the way it's constructed, it doesn't particularly care as to what causes the trigger. What you will get, of course, is feedback to say it's operated and how many times it's operated. So you can correlate that against your models to find out if there's something also adverse happening with the network. So if you find, for example, the regulator's operating when you expect it not to operate, you can suspect perhaps there's a blockage building up somewhere down in the network, which is causing the sensor to trigger the closure of the regulator prematurely, and when it shouldn't be closing, because obviously the network isn't genuinely loaded, but that could be an indication there's actually a fault somewhere in the network, i.e. some form of blockage building. So there's other things that will come out of this application. And it sort of then spins on to other applications around this. We mentioned earlier about the potential for flushing, and that could become a regular thing where, for example, once a month, you'd have a control strategy that says, let us build up the level and then flush. And it also comes on to another thing that's not perhaps been mentioned earlier, is the fact that David mentioned the wet wells. But if you took the Southwood and Ferrers example, the traditional solution would have been perhaps a wet well, which would have filled up and then had to be pumped. We've actually eliminated the need for pumping. So we've actually made it very carbon negative in terms of, by comparison, to having a wet well and pumps and the maintenance of the pumps thereafter. So we've not actually had to build a wet well. We haven't got the chamber. We don't have the septicity and smell problems. We don't have the maintenance going forward. But more importantly, we don't have that carbon used to pump the water. And I think that David would say there's a lot of pumping stations around Anglia, being a very flat catchment. It's tens of thousands, I think, if I'm correct.
30,000.
Many thousands, yes. So it is a big consumer of energy. And I think someone gave me a statistic once saying the water industry now in the UK is probably one of the biggest consumers of electricity, which doesn't surprise me when you look at what's required, from the point of filtering the water to deliver to your door, and then taking it back round, pumping it, filtration, purification, and then discharge back into a river. There's a big cycle there, and every bit that can be done to reduce the energy consumption is a bonus.
Okay, thank you both for the brilliant presentation so far. So the time is now 11:05, so we're just going to go to a final 10-minute break, give you all the chance to kind of get a hot drink if you wish, and then at 11:20 we'll return for our question and answer session. Thank you, everyone. Hi all, I hope you enjoyed your short break. So we're going to return to our session with Radio Data Networks now, and we're heading into our Q&A session. So if you do think of any more questions while we're discussing the answers to what we already have, please feel free to pop them in the chat and we'll try to cover what we can. If we don't manage to get around to answering any questions today, they will be uploaded, and any unanswered questions will be uploaded to our platform alongside the case study and the showcase recording after today's session. Okay, so first question from Martin is, have you considered issues with times of retention of foul/combined sewage?
The answer is yes to that one. We have. When we initially looked at using the flow control valve, we were contemplating, it was for a small development, something like 30 properties in the first instance, and we were looking at the volume of flow generated from the number of connected premises, and obviously doing some dry weather flow calculations. We looked at the volume of flow on a dial curve. We decided if we wanted to avoid creating impact on the downstream sewer for the duration of a wet weather event, we should maybe provide sufficient storage capacity to hold the volume of flow generated by those properties for a period of 24 hours. So what we did was looked at the proposed sewer diameter and length that were provided by the developer, and asked the developer to upsize the sewers in terms of their diameter to facilitate that capacity being held back for that 24-hour period. Obviously, that gave us a further concern about potentially sedimentation and odours developing over that period of time. But with evidence-based understanding of the likelihood of the wet weather events that would occur in that location, not usually exceeding more than sort of between 1 and 6 hours, we didn't think that would be a problem. But yes, that was contended.
Actually, to back up David's comment there, one of the beauties of the sewer flow regulator is, as you saw in the illustrations, is the speed of its opening. So unlike a penstock, which opens very slowly, these open quite fast, and therefore you do get a flushing event. So that helps to then clear out the backlog of accumulated sewage. So it's a double thing. You know, you've got a fast closure, you've got a fast opening, and the potential for flushing, and therefore it helps to clear itself out after the event has abated.
Perfect, thank you. And then Melissa has asked, has the installation been tested in situ when jetting ops have been undertaken? Does it withstand?
So in terms of, sorry, I didn't quite get the context there.
So I guess she's asking, does it withstand jetting when operating?
Oh, jetting, beg your pardon, jetting, yes. Yeah, so jetting is something we would suggest is avoided. To actually jet the entire assembly, no different than you would on a sensor. So if you had a sensor in the network, you wouldn't jet one of those, because as everyone knows that's seen a jetting team at work, they will cut through cables and all sorts on sensors. So jetting, yes, it can withstand it potentially, but something we wouldn't advise, simply because we have got gaskets and seals and so on, and actuators in terms of the control airlines and so on, which could be cut by a jetter. But the actual body of the elements are stainless steel, therefore they will be immune to jetting. But also think about the benching. Benching is quite soft. If you're going to start jetting out a chamber, you could start eroding and scouring the benching. So it's something that would be avoided. If you're going to do it, you'd do it at a lower pressure than normal, for certain. But something I wouldn't recommend jetting.
Thank you for the answer. So then Tish just wants to know, great to see practical applications of smart real-time solutions in sewer networks, and has a couple of questions about it. First of all, he wants to know, we have found that ascertaining the right locations is the real key for such solutions. So how are the locations of the valves are sited, and how is the control logic determined, as there is need to ensure the problem is not shifted elsewhere?
Yeah, that's an interesting question. It's very relevant. In the instances where we've already used the flow control valves, the location's been determined by the development itself, and they've been relatively small scale development. So we knew where we wanted to site the valve to control the flows, and the sensors that we wanted to use to power activate the valves were located at the hotspots Brian's already mentioned. Those points in the sewers where surcharge can occur quite quickly, and those levels are noted, and we set some critical levels that we don't want to exceed if possible, and reduce the flow entering the downstream sewer by controlling the valve, actuating the valve, and preventing those flows from the development and reaching that spot at that time period. Obviously, when the flows subside, the levels subside in the sewers, we then release the flow from the development site and back to normal. I think Tish's point is that we do need to use the hydraulic models and a wider understanding under a variety of wet weather events to make sure we have the proper understanding of where are the most appropriate places to locate the control sensors that would actuate the valves for the flows we're trying to control and manage.
Absolutely. Do you have anything to
No, I actually agree with David. I think that's very important. I think the other thing that's quite important is also to look at response times. Some catchments are very flashy, others are less flashy, and that will have a great influence on the choice of sensors, the type of telemetry, and how that's powered too. So if you're looking at a battery-powered telemetry solution to measure the actual levels, that may not be viable if you find you've got a very flashy catchment, which will then respond in a few seconds. Whereas if it's one that responds slowly, then battery power would be viable. So it's a bit of horses for courses. You have to really understand the flow dynamics, the response times of that catchment. How much time have you got? Because as you've seen in the demonstrations, the regulator actually operating is very fast. So unlike a penstock, which takes several minutes to close, these will close in a few seconds. It's typically 5 seconds from open to close. But you do need a fast sensor, and hence that's why we talk about real-time data and the need to get the signals back very fast. And also the sensors could be at multiple points, so you don't have to necessarily rely upon one sensor. You could have several in a catchment, and it could be any one of several sensors trigger, or you may have an OR function, excuse me, which says if sensor A and sensor B go off, they're above high level, then you need to close the regulator. So it can be one where you want to have it dual redundant or single redundancy. All of that can be achieved.
Fabulous. And just following on from his question, he also asked, are there any issues encountered in terms of odour or sedimentation?
To date, we haven't had any reported issues with those. I mean, but again, good points, because obviously, if the volumes of sewage are retained for a period of time, there's a possibility that odour could occur because of the sewage turning septic. I mean, obviously, we don't intend or plan to do that to happen. It could happen, and sedimentation similarly could occur. But obviously, we try to take into account by the gradient of the sewers that we do achieve self-cleansing. And that we don't have any build-up over time in that sewer length upstream of the valve.
Yeah, I suppose to follow on from David's point, also you have to look at the alternatives. So the alternative would be, for example, a wet well and rising main. They always have an odour issue associated with them. And equally, if it was a penstock, apart from the issues we mentioned earlier about getting mains power for the penstock, you'd have a similar setup with a similar chamber, similar retention. So we're actually not any worse than we would be on any other technology. I think it's this, but we do have the benefit of that speed of opening, which does, as David quite rightly mentioned, give you the ability to flush through the network. So you do have that extra bonus.
Absolutely, thank you. And Melissa has asked, I imagine this could result in an it depends kind of answer, but what is the kind of latency you can expect between signal and action?
Okay, perhaps I'll answer that based on the telemetry side of things. It entirely depends on how often you want to send the message from A to B, from the sensing point back, and the type of sensor used. But as you saw in the live demonstration, we used a Vega radar, which has a typical response of 10 to 15 seconds. If you link that to live telemetry, as we had in the demonstration, then you could be talking about a 15 seconds to 30 seconds response. But that would be a system that's running off solar or with solar assisted battery, so a kiosk by the side of the road, for example, and a sensor in a chamber. Alternatively, if it was battery powered, of course, then the delay, the latency would increase, because you'd have to then wake up a sensor, go to sleep, and conserve power to make it battery operable. And so that's the real two constraints you have. It's how much power have you got at the chamber side, where the sensor is in terms of the response. But as you've seen from the demonstration, the regulator response itself is very fast. It's sub 10 seconds from receipt of message to closure.
Perfect, thank you. And she also just wanted to know, have you also tested this in a scenario where you might have a number of these in play, and how do you manage it at a system level?
So we haven't had several in one catchment, but we have had similar systems where we've had multiple pumping stations which are inhibited using our telemetry. And you'd have a similar scheme that's used on the telemetry, where you can actually stagger the operation of each of the regulators. So what you don't want is 7, for example, regulators all to open at the same time, creating a little tsunami down the sewers. What you can have is a timer in a control central point that says number 1 open, number 2 open, and so on, in a sequence, allowing for the transit times down the sewers. And this is something we've done actually with Anglian and Northumbrian Water on pumping stations, where they use their algorithms in their control PLCs to provide that particular stagger for pump inhibit systems using sensors.
Yeah, just to add to what Brian mentioned, I think we're in quite a healthy position in water industry now, because many water companies, Anglian Water included, are putting a large suite of sensors into their sewer networks so that we can understand the flow patterns. Usually they're going to be level sensors, so we don't have the luxury of flow. It's more expensive to flow velocity. But with an understanding of the level sensor, we've got the understanding of what percentage of the sewer capacity is being used at any point location in the sewer network. And as Brian mentioned, what we're trying to do, and I think this was alluded to, is make best use of the sewer capacity by understanding the travel times of the sewage, the transit times between points of the sewage in the network, and operate the valves accordingly to make best use of that capacity. I mean, it's clever stuff, and hopefully we're getting there, but we're still a way off at the moment. But obviously we're entering into the world of digital twins and AR representation of our networks, rather than the older deterministic models, hydraulic models, which are very good. But with the advent of the lower cost sewer sensors, we can feed back all that information into a control model, which allows us to take quick action and do it iteratively using feedback principles.
Fabulous, thank you both. Following on from that, Martin wanted to ask, the installation relies on the seal between the benching and the blade. I'd expect some leakage in real world applications. This probably isn't enough to matter in flow control situations, but I guess this device isn't applicable for pollution prevention scenarios.
So Martin is absolutely right. Yes, he's spot on there. We would never expect 100% seal. Our target with the first installation was to achieve the high 90s. And yes, you saw the example out there in the plastic invert where we did actually get 100% seal. So for pollution prevention, no, but we do have other solutions for that, which are not featured here today. So we have total retention, pollution and containment valves, let's call them valves at the moment rather than regulators, which will fit on outflows and so on. But as soon as you're into the world of 100% sealing, then you're talking about having a seal at the bottom and you're back to a frame type of assembly. But what has to be thought about also, if you compare a penstock versus what we're doing now, if you look at the EA guidance on testing of penstocks, they are actually allowed to leak. There's a permitted leakage rate depending on the seal circumference. So even a penstock, which people think don't leak, are designed, or not designed to leak, but actually will leak by the nature of their design, because they're not actually imposing significant force on the actual gaskets in the seals. So nothing's infallible unless it's designed specifically for that purpose. And yes, a pollution prevention type of device is available. Similar operating strategy, but you mainly find these deployed on industrial sites for pollution, spills, fire, water containment, and so on, particularly on surface drains. Whereas what we're talking about here is an application in sewer networks, where you're talking about regulating flows rather than stopping the flows. And to get a 90% reduction in the peak flow, for example, as a target, is more than enough usually to prevent an overwhelming of a sewer network further downstream.
Thank you, Brian. So just wanted to know, are there any restrictions on sewer diameter?
Absolutely, and he's absolutely right again. You wouldn't want to regulate and control a very large sewer, because that's again putting all your eggs in one basket. As we sort of started off the discussion earlier on, we've coined the word lateral flow modulation, where we're talking about laterals. So it's the sewer laterals we want to target. It's those smaller pipes, not the large main sewers. Because if you haven't got storage necessarily in the main sewer, but you've got lots of laterals with potential capacity for sewage storage. And also you've got the ability then in the laterals to, as was mentioned earlier, to stagger the release. If you've got lots of laterals in a catchment, all of which have a regulator on them, you've distributed the problem, you've distributed the load in, and you've actually then got the ability to stagger the discharge later on downstream. So I wouldn't advocate a very large one. I would be more in favour of several in a catchment, smaller discharges which are regulated.
Fabulous, thank you. And then Mike from Xylem just wanted to ask, what are the results of maintenance on these valves? There seems to be a lot of moving parts on the valve construction that could possibly get exposed to the waste in the flow. And when maintenance is needed, it looks complex to maintain. How can that be handled by low/non-skilled labour forces?
Well, part of the intention of the design was to make it very simple to maintain. As you saw in the earlier demonstration, the regulator blade is removable, but also what hasn't been sort of perhaps mentioned earlier is the wiping nature of the construction. So you saw there was a stainless steel scraper actually wiping up and down against a HDPE tongue. So effectively the tongue, the regulator part, is a plastic part which is wiping against the stainless steel back scraper. So it's actually got a self-cleaning mechanism. Now, to be honest, to date, we don't get involved in the actual maintenance of the valves and regulators. But having said that, I think David will confirm with this, we haven't had any call-outs either. We do have to emphasise that all of these installations were started and commissioned during the COVID period, so feedback wasn't particularly good. But to date, what is in service, we believe is working, and what we believe hasn't maybe needed to be maintained or not, we're not 100% certain about that, which doesn't sound very good, but no news is good news in the respect that we haven't had any adverse stories about things needing a lot of maintenance and blocking and so on.
Absolutely.
So I think that's where we can leave that particular one at the moment.
Perfect, thank you. Brian, did you have any, sorry, David, did you have any thoughts to add to that?
No, just to concur with Brian.
Perfect. So following on from that, Mike also wanted to ask, why did you design a whole new valve? Are there no standard valves on the market already that could have been used within your control system?
The the standard valves on the market require a frame. So if you look at the penstock construction, it has a frame and it relies on a top and bottom sill. So that's a very good question, because straight away you then have to break into the invert to make the installation. As soon as you break into the invert, you're then creating a discontinuity, which then comes back to the previous questioner's question about fouling and causing rags and debris to build up, and it's increasing maintenance. So as you saw in the demonstration, we haven't touched the existing invert. That's where the sewage flows. Because what has to be remembered, these may not operate very often. It may be once or twice a year when we have one of these big storm events where they have to operate. And therefore, you don't want an unnecessary risk in the actual sewer network. And by having it sitting above, poised to pounce on the actual flow, and not touching the invert and not making a discontinuity, is the key. As part of the pattern, the way we actually use the invert as part of the sill. And there was nothing on the market that did it in this way, and included the overflow chamber and the body, because we needed an overflow chamber as well integrated within the design. So if you look at the standard penstock at the moment, to use a penstock in a similar application, you need a new chamber, you need to build a weir wall in the chamber, you have to cut into the invert by comparison, and that's probably the nearest equivalence we can find. Obviously, the penstock requires mains power as well, which is another challenge to get power to the actual site. Yes, you can get solar power penstocks, but they are very slow and sluggish, and they require very large solar panels. One of the key parts of this design also was to make it very lightweight. So as you saw, it was easy to hand carry. And by making it lightweight by virtue means we actually use substantially less power. And we've done some rough calculations compared to a penstock of a similar size. We believe it takes 1/50th of the energy to operate this device, which then means it's very solar operable, which is another hidden benefit.
Fabulous, thank you. So Andre wanted to ask, if the solar panels were vandalised at any point, how long can the valve operate normally?
Okay, so obviously it would be subject to the operational cycles and how often they're used. And it's a valid question, but fortunately to date, we haven't had any of the sites vandalised. But the solar kiosk actually includes some extra features which are hidden away there. It's got a built-in detection circuit, which actually detects if the solar panel's been vandalised. So it detects the fact that you don't get a charge during the day. So during the day, every time the solar panel even gets an overcast view of the sky, you'll get a signal to say the solar panel's intact. Conversely, at night, it will go off to say that it's not. So you get a positive change in state. So the solar panels are monitored. And going on to the actual question, depends on the size of the battery, but it's viable to have several months of operation of the system in standby, and circa probably 30 to 50 operations on the battery. So normally we'd have, say, 100 ampere-hour battery in the bottom of the kiosk, and that would be more than adequate for 3 months of standby, and perhaps up to 50 operations.
Brilliant, thank you, Brian. So Mike wanted to go on to ask, you mentioned at the intro that Edge/AI was part of the requirements. Could you highlight how artificial intelligence has been applied in terms of learning from the data streams?
Absolutely, yes. Thank you very much, Mike, for asking that question, because it's given me the opportunity to use a phrase which I had to practice saying several times over to make sure I got it right. And I hope it makes me sound intelligent, probably doesn't. But obviously, in the days where data is king, and it's very important indeed, over 10 years ago, I started looking at the use of multimodal models using genetic algorithms, backpropagation algorithms and fuzzy logic for the purpose of predictive and preemptive understanding of our hydraulic networks. So that data is very, very important. The issue is obviously within our business, we have data. I mean, primarily it's a lot of data from things like pumping stations in terms of their operations. Moreover, now we're getting data from flow and level in sewers, which is very good, and also data from the operation of our overflows. But the issue is obviously bringing the data together to make best use of the data, and that's obviously the challenge. At the moment, we're all water companies in the process of building representative models using effectively digital twin technologies and so on to understand what's happening and how it's happening and what we can do best. And I think we're all still in the learning phase. And over the years, I'm going to be able to make better use of that data to be able to better control things like the flow control valves that we're offering up with Brian's technology.
Perfect, thank you, David. Brian, did you have anything to add to that at all, or?
Okay, I suppose the only thing I could add on to this is if you're using artificial intelligence, it's making these sensors have even more intelligence, so they know when the decision point is required. So you can move the point of control away again from the central coordinated control area, and it's having edge computing within sensors, as we do with some of the sensors we've used on some of these projects. So they have a affirmative check to make sure, yes, the level is really, really high. So if you're getting turbulence in the flow, what you don't want is the thing to oscillate and switch on and off. So you build some hysteresis in, if you're using level sensors and so on, so you would have edge computing. The control panel also can have a degree of edge computing in there too. So it can be autonomous. He has the ability to make decisions. And it may be a question that turns up later because no one's asked is, does it know if it's working? Yes, it does. It has feedback, it tests itself. And as you saw, it uses pneumatics, it tests the airlines for integrity, tests for leaks and so on, and will feed back the fact it's had an issue and fail safe. All those sort of things are included within the smart control. But one of the things that hasn't perhaps been highlighted, a lot of thought and design went into the actual control panel, was one of the big issues is if you were to use a standard PLC controller, they eat a lot of power, have a very high power burden. And again, to get solar operability, you can't afford 100 milliamps to be sunk by the average PLC controller. The controller we've built for this project consumes just a milliamp in standby. So it's a very, very low current controller, was part of the keys to actually make this project successful. So if you tried to run it from a PLC, as I said, you couldn't run it from solar. You've got simple state controller in the control panel that controls the sequence, able to open and close, detect faults and so on, and respond back by saying I'm open, I'm closed and so on, and connect to telemetry. It's all part of the equation. You've got to get things low power, low energy and so on. And that then means you have a viable, retrofittable smart network element. One of the other things that hasn't been mentioned, of course, is you can use these also for temporary deployments. When works are being conducted, you need to temporarily divert flows, because again, you're not talking about significant amounts of installation cost in comparison to fitting a penstock or another alternative. So there are other options and applications that arise because of this simplicity of installation.
Perfect, thank you. So Andre just wanted to know if the valve, I think you've just covered this slightly in that question.
Okay.
But if the valve opens to fails to open or close, will a failed signal be sent to telemetry?
Yes, so the answer to that one is a yes. So it will know it hasn't happened, it will know it's stuck and so on. So there's a means of feedback to say what's happened, and a lot of it's measured, and actuation is measured by the changes of pressure in the actual system. So we monitor that very closely. So the answer is yes, and the signal can go back by a number of means. It can go back as a volt-free contact to an existing telemetry system, or alternatively, it could go to a cloud, should a client wish to have a cloud-based solution. But
thank you.
that's it.
So Martin wanted to know if you fit a containment weir on the spill pipe from the CSO, the operator would need to pump any contained spill back into the combined sewer before it's reopened. Is that correct?
I'll do a bit of this first and David can follow. So on a long pipe that comes off the end, obviously the preferable location is at the weir where the CSO is actually, the actual CSO is. So there's a CSO is in the actual sewer network, and there's a long pipe that leads off to the point of discharge. So preferably you would want to install the regulation or control at that particular point. But if you can't, then end of pipe becomes the point of last resort. It's still better to do something there than nothing at all. But then the regulator or the weir is set forward in such a way that it actually captures the pollutant, but also makes it so it's accessible by a tanker. So you wouldn't pump it back into the sewer network necessarily, or you could. It would be generally tankered away. And there are examples of that type of technology installed elsewhere in the network where we've actually built that type of system set slightly forward, so you don't have to put the pipe up, the tanker pipe up the actual overflow pipe, but it brings it slightly forward.
Perfect, thank you. And again, I think this has been slightly answered in previous questions, but just to see if you've got any extra thoughts to add. Edmund has asked, how reliable have the regulators been in service? What are the extra maintenance requirements, and how widely do Anglian see themselves using these regulators, e.g. how many sites/units?
In terms of reliability, we have a handful in operation. I've not had any reported problems or issues with them to date. Brian and I have decided what we need to do is go and have a look, review how they're performing, get some feedback from the operators, and check for ourselves whether they're still operating as they should do. We believe they are. At the moment in time, they're not linked into our corporate control, our SCADA system, and that's something I think for the future we'd like to do, so we have an awareness of what's happening, their operational status, and so on. And that's certainly planned. In terms of rolling out, extending the network of control centres, that's something that has to be considered because they offer such great potential, as they are relatively expensive and easy to install. And they're particularly suitable for things like small new developments. We can ask the developer to consider installing that cut-in device rather than putting small pumping stations, which are very onerous for water companies to operate and maintain thereafter. And a network of flow control valves would give us the opportunity to effectively play tunes with the available capacity in the sewer network, provided we have an overarching model and way and means of carrying out that control. So yeah, there are great possibilities, and particularly with respect to our challenges regarding water quality and operation of CSOs. I think it's obvious that this is a way forward. We're doing things, as I mentioned before, controlling things like first valve flush to some degree to help and enhance the water quality in the receiving rivers. So yeah, there's opportunities.
Perfect, thank you. Brian, do you have anything to add to that at all?
I can concur with David, really. I think, again, I always go back to the maintenance is linked to what is the alternatives. You've got to do something these days. You can't let pollution occur anymore. And the alternative would be this versus pumping stations versus penstocks. And you're always going to have some degree of maintenance required, whatever the solution is. And this is no worse than anything else. So I think you use it in comparison. But you are looking at something that also has the added bonus of being a very low carbon intervention. So in its lifetime ought to be then more carbon friendly.
Absolutely. And that leads us nicely to Melissa's follow-on question from that, which is, do you know yet the expected lifespan of the unit or component parts yet?
Okay, that's a very good question. But that, I think that sort of allies with the sewer itself, because sewers get eroded by septicity and so on. It's a very difficult one to judge, but we would anticipate at least a 10-year service life. But the moving parts can be interchanged. So we see the regulator part, the moving parts, the bit that could potentially wear as being a service replaceable part where it could be serviced, cleaned, upgraded. And if it's a standard size, which the body part is the variable and the blades are the fixed constant, then there's no reason why you can't have interchangeable parts. So unlike I suppose one of the big differentiators here between a penstock, you've got to take the frame out. You have to dismantle the whole penstock. It's a big confined space entry project. Whereas the regulators, because they slide in, slide out of their grooves, you can take one out, drop one in. You don't need a return trip. So you can service, take out for service, clean one, put a new one back in there and then, take one back for refurbishment. You cannot do that with a penstock. You've got to go for a period without any protection while the regulator's away or the penstock's away for service. So I think that's a bigger USP that's come out of this discussion, but perhaps hasn't been considered. The serviceability and the cover whilst things are out of operation. And the same applies to pumping stations. If a pump goes offline, you've got the problem. You have to come in and then replace and swap, which you would do on a pumping station. But I don't believe you can do that so quickly and readily on a penstock.
Absolutely. Thank you, Brian. So Ricky wants to know, what frequency does the radio link operate on?
So that's an Ofcom licensed channel. So we do keep that closely guarded secret. All we can say is it's VHF. It's protected spectrum and it's protected under the Wireless and Telegraphy Act against interference and jamming and so on. But we can actually put it on any frequency. So if a customer has their own license, which we would always recommend, licensed channels in preference to license free, it can operate on anything. So again, we've said it's agnostic. Any system that produces a default-free digital contact can operate the system on an analog level. So we're not particularly prescriptive about that. But in our case, we have our national Ofcom license band, which covers the whole of the UK from the Channel Islands right the way out to the Outer Hebrides and Northern Ireland and so on. So we can operate it securely on that particular band, but it doesn't have to be. We're not prescriptive about how things are done. We need compatibility with what the utility is already doing.
Brilliant, thank you. And related to that, Oliver wanted to add, are you able to have multiple in close proximity without any cross communication issues?
Absolutely, yes. Again, that's the same thing. Because we own the spectrum, we have total control. So it's unlike LoRa, where you can have anarchy. I look at it now as a bit of the Wild West, because you can have tens of thousands of sensors in the same area. We're not talking about tens of thousands of sensors here. We're talking about just a few. And we have 4 billion combinations of encryption codes on these. So the two will not interfere with each other. And we have enough evidence now that this doesn't occur, because Anglian and 7 other utilities are using this spectrum, or using this to deliver about 500 million messages a year. And we've never had a reported issue of cross talking. So a lot of these telemetry systems we've been deployed have already been used for pump controls, pump inhibits, for pressure regulation in sewer networks, and drinking water networks, and so on across the UK. So it's not like it's unproven technology. So the radio part is very proven, and that was our background actually. So if you wind the clock back to my personal background, the last 30 years has been building radio telemetry systems. So it was always from a background of monitoring and delivering information. And it was really the inspiration of what David said and what we've had since 2015 about, rather than just monitoring and hearing all the stories and tales of woe about CSO spills and so on, it's actually now applying real-time data to produce control. Hence the sewer flow regulator was born, or the wastewater regulator was born out of that need to do something about it. It's like having the analogy, you've built lots of these sewer monitors around the country. It's like having lots of speedos on cars, but we needed the brakes. These are the brakes now, which will take us to the next stage of actually improving water quality, CSO spill reduction, which monitors in their own sense can't do. So that's where we've sort of gone with this journey.
Perfect, thank you. So again, this kind of relates to the questions. I'm sorry if you've sort of already answered this.
No problem.
But Andy wants to know if any sort of cybersecurity measures are included within the control system, how it communicates with the endpoint devices, and around signals or control actions sent to the local system from a central control centre.
Yes, so obviously we won't go into how the security is implemented, but one of the main criteria is the fact that we're not using an IP system. We're not connected to the internet in any way, shape or form, which innately makes you have a high level of cyber security, because there is no cyber attack that's potential from anywhere in the world. It's a local system, and it is actually protected. So if you look at the most basic type of attack, with someone trying to jam the system, you can't even buy equipment on the right frequency off the shelf. You've got to know where it's operating. Because we're sending tiny packets in frequently, then someone's got to sit there for a long while in the catchment trying to work out where the actual transmissions are occurring. It will take literally probably a lifetime to scan the entire spectrum from a few kilohertz to 40 gigahertz. There's a lot of spectrum there, and we're somewhere there. That's why we won't advertise openly where we operate, for that reason. But also have to consider the other options. And also the other thing is, most important is, when you look at cyber, one of the biggest problems, as Tim Davis-Lee, I think his name was, that invented the internet, said, you publish the handbook. So the Haynes manual has been published on how the internet works. So it's made it very easy. All someone's got to do is find the key to the door. With this, it's completely different. You've got an unpublished protocol, you've got a hidden frequency. You don't actually know where to start. So you've got to build a lot more things before you could even consider it. But who's going to bother? They've got to be in the catchment 24/7, 365 to do something. It's a localized autonomous control. That's the idea of autonomy, which is no different to the same threat about autonomous vehicles. You've got to keep it itself. And if you're off the grid, off the net, then you've reduced your risk substantially. But the final part that sort of spins off of this also is the fact that this is a protected system. It's protected in law, unlike Wi-Fi and so on, and LoRa and Sigfox and all those sort of things, which are not protected at all in service. These are actually protected legally under the Wireless and Telegraphy Act. And I think there's actually a potential for a 6 months custodial imprisonment for people deliberately interfering and breaching the Act. And also you can get a £10,000, I think it's on the spot fine, for deliberate interference. So there is some draconian penalties there, and rightly so. But the fundamental thing is the obscurity that you're starting with, and the fact you can't go down the road and just buy off the shelf something to talk to this network is not available.
Thank you very much, Ryan. So Oliver wanted to ask, you mentioned the general idea that they're only used a couple times a year. How do you define the levels in the downstream network at which point the system operates?
Okay. Well, again, I think it's been touched on by previous questions. We have to have an understanding of where the surcharge locations are, where our sewage tends to escape when we get hydraulically overloaded in the system, and those are the places we'd like to locate our sensors, level sensors, detect the point in time at which we need to take action by closing off that valve. Obviously, by the time the sewer has become surcharged to a certain degree, it could in some circumstances almost be too late. But if you site your sensors appropriately to give you an understanding of things like the rate of change, rate of fill of the sewers, and an understanding of what point in time would the sewer become surcharged, you can take appropriate preemptive action by holding back flow at the control point with the control flow valve in sufficient time to make sure that those sewer volumes that you're holding back don't adversely affect the capacity downstream.
I suppose following on from David's comment, there's also the ability to, because we're not fussed about the type of sensor used, you could use rainfall indicators and distrometers and things like that to trigger the closure as well. So even a heavy, intense rainfall incident, you could close the regulators then. So it would be another opportunity. And I think it's a matter of mixing the type of sensors, because as David quite rightly says, there's a transit time down the networks, which can mean that you don't quite know what the level really will be, because it's going to be in the future sense, because your sensors have a delay and a lag. But also it's then being smart about the network and then placing sensors further upstream, which may not be at the critical pinch point, but they'll then reflect the level which would occur later, perhaps 10, 15 minutes later downstream. So it's a matter of the network modelers, the people who understand the flows in the catchment, working together to produce that information and then positioning the sensors. And there's no hard and fast rule that says you put the sensor at point A, that you then don't move it. You can move it and relocate it.
Absolutely. Thank you for that, Brian. So a couple of final questions. Can you design these valves to fit into different sewer types and sizes, and sort of how would you go about that?
So we touched on the procedure for fitting into different shapes and inverts and so on. One of the key parts is to obviously template the actual invert so you get a shape and profile, because as we mentioned and alluded before, sadly all the inverts are hand built and everyone's different. Particularly if you're retrofitting to an old sewer, you're going to find a huge variations in sizes. And it's not just the shape of the chamber that varies, it's the angle of the way the invert flows through the chamber and so on, and the height of the benching. We found tremendous variation in that. And there is no rule that says you can't grind it flat if it was a bit uneven too, because sometimes the cement in the benching is being daubed on by hand and not particular attention, because no one's ever going to see it to make a perfect finish. You can grind it off flat should you wish to do so. But one of the key things we have to emphasize is it's important to keep the flow flowing. So you can modify the benching on the top, but what you're not doing is changing the invert. So therefore we work with the back wall, we'll make the chamber that's at the back, the overflow chamber, fit the back wall, or alternatively, as you put in the illustration, it would have set forward weir wall in the chamber. So there's two options of mounting there. And again, that would be made to fit the basic contours of the benching, and then benched in further around it to make a sill. So you can adapt. It's an adaptive design where we have the fortune, I suppose, of manufacturing and designing everything in the UK. Means that we keep the lead time short, and we have the ability then to adapt the designs to the customer's needs, as we have on all occasions so far. Everyone has been different. But the variation is about the mounting on the benching.
Thank you. Great answer. So I think, again, already been slightly covered, but can this be fit onto CSO overflows at all?
So we've sort of touched on that before, and the answer is there's a variant of this that can go on an overflow, preferably at the actual CSO itself rather than at the end of the discharge pipe, so you don't have a pipe full of sewage. But if it has to go on the end of the CSO pipe, it can be there, mainly to provide a containment vessel for someone to tanker away the captured pollution. So you have to consider the impacts of having I think if I'm correct, is a category 1 pollution incident versus a category 4, which you can turn one into the other by having the containment on the end. So it's a difference between a fine and not a fine. will be the cost of a tanker.
Amazing, thank you. Okay, so that brings us to the end of today's session. I just wanted to take a moment to thank Brian and David for their contributions today. It's a really great presentation, and a lot of thought and time and effort went into the live demo that was delivered today. So thank you so much to Brian and the team at Radio Data Networks for providing that. Thank you to the audience for taking time out of your day to come along today. We hope you found it valuable and that you found some valuable knowledge to take back to your organisation with you about this technology. If you have any further questions, do feel free to get in touch either with Spring, or I'm sure Brian will be happy to answer any further questions as well. I think you've said you're happy for us to pop your email in the chat.
Absolutely, yes.
So feel free to get in touch with Brian. We'll share his contact details in a moment. For anybody who would like to watch the recording back at all, we will be aiming to upload this onto our platform within the next week, along with a written case study and any sort of questions that we didn't get around to answering today. I think you'll have seen, but my colleague has put a poll into the chat too, just a quick couple of questions, just so we can gauge how valuable you found today's session. And your feedback is really appreciated. So if you could take a moment to answer that poll before you leave today's call, that would be much appreciated. So thank you again to everybody involved today, and have a lovely rest of your day. Thanks all.
Thank you.